Acids and bases. We're going to begin our study of acids and bases by learning about two different theories of acids and bases. The first one is probably familiar from grade 11, the Arrhenius Theory. According to Arrhenius Theory, an Arrhenius acid is a substance that dissociates in water to produce hydrogen ions. And so you'll notice that HCl breaks up into the hydrogen and chloride ions, and it's the presence of this ion that indicates that HCl is an Arrhenius acid. Now, I'll actually just adjust this dissociate to ionize, just to make a distinction between those two terms. A substance that is a molecule, so HCl, which is a molecule, that then forms ions, technically that molecule ionizes to form ions. A substance like sodium hydroxide that I have in the base example, this is an ionic compound. It's already present as ions. Those ions just break apart, and therefore that is the process of dissociation. So we'll say that an Arrhenius acid ionizes in water to produce the hydrogen ion, and an Arrhenius base dissociates in water to produce hydroxide. So you'll see that sodium hydroxide here produces the hydroxide ion, and therefore sodium hydroxide is recognized by Arrhenius theory as a base. I've given you a third example here of sodium carbonate, and I've written the dissociation equation. You'll notice that we have sodium ions and carbonate ions. So does Arrhenius theory recognize either sodium carbonate as either an acid or a base? And the answer is no, because we do not see the hydrogen or hydroxide ion being formed. And yet, sodium carbonate solution, if you test it, will have a pH of greater than 7. And so the Arrhenius theory itself, although it's a good basic theory, is not enough to be able to explain the properties of all basic solutions. And so we move on to a new theory, Bronsted-Lowry Theory. This is the more challenging of the two theories, and it's where we spend the bulk of the lesson. So according to Bronsted-Lowry theory, an acid is a proton donor or a hydrogen ion donor. So let's review way back to grade 9 here for a second and think of the hydrogen atom, mass of 1, atomic number 1. So we have 1 proton in the nucleus, subtract the mass minus atomic number to get the number of neutrons. 1 minus 1 is 0, so there's no neutrons. And then we have 1 electron. Now, when you form the hydrogen ion, we essentially lose that 1 electron. And so the hydrogen ion with a charge of positive 1 is really just a proton. And so you'll see in the definition of Bronsted-Lowry theory, when we say an acid is a proton donor, you could also view that as a hydrogen ion donor. So you're going to see H in the formulas. Really, it's the nucleus of the hydrogen atom, so the proton, that is being donated. So what does that look like? Well, here I've drawn, as you can see right here, a water molecule in the presence of a hydrogen chloride molecule. And the hydrogen in the HCl behaves as a proton donor, or H positive donor, when both electrons from the oxygen of the water grab the nucleus, the proton of that hydrogen atom. These electrons both stay with the chlorine atom, and so that water, which originally had 2 lone pairs, now is making a coordinate covalent bond to the hydrogen nucleus. In other words, both electrons in that bond, I'm referring to this one right here, both electrons in this bond are coming from the oxygen atom. And in doing so, because only the proton came with the hydrogen and not the electron, we now are actually short 1 electron. And so this structure actually has a positive 1 charge. Now what happens when both electrons stay with the chlorine atom? Well, it originally had 7, now it has hydrogens, electron, and so we've now formed the chloride ion. And so we can complete our equation here to write H3O positive and the chloride ion. So what's the name of this H3O positive species? It's called the hydronium ion. All right, so HCl and water combine to form the hydronium and chloride ions. So HCl behaved as a Bronsted-Lowry acid because it donated a proton. So if you compare the HCl to the particle that's left behind once it donates its H positive, you'll see that we've formed what's called the conjugate base of HCl. And so this is a conjugate pair. So HCl is the acid, and when it donates the proton, the particle that's left over is the chloride ion. So the chloride ion is the conjugate base of HCl. Okay, before I talk about the water in that example, I'm going to move on and define a Bronsted-Lowry base. So a Bronsted-Lowry base is a proton acceptor, or an H positive acceptor. So have a look down here at the ammonia example. The lone pair on the nitrogen is going to grab the hydrogen nucleus from the water, that proton, and the electrons will stay with the oxygen that is still bonded to another hydrogen. And so that ammonia particle, previously having its 3 single bonds to the hydrogen, now is making a coordinate covalent bond to the proton from the water. Since the electron from the hydrogen did not come with it, we actually are short 1 electron. We have 1 more proton than electrons in this entire particle. And the oxygen now has an extra electron with it, and that came from the hydrogen, and we formed the hydroxide ion. So you'll see that ammonia and water then react to form NH4 positive, the ammonium ion, and the hydroxide ion. So, conjugate acid-base pairs here. Well, the ammonia is behaving as a Bronsted-Lowry base because it is accepting a proton. What's the particle that's formed when this base accepts a proton? Well, it forms the ammonium ion. And so the ammonium ion is the acid in this conjugate pair. So I'll say that again. The ammonia acts as a Bronsted-Lowry base by accepting a proton, or H positive, and in doing so, the particle that it becomes is the ammonium ion. Okay, now what's water doing here? Notice the behavior of the water. The water is actually donating a proton. It's donating the H positive. And so water is actually behaving as a Bronsted-Lowry acid by donating a proton. The hydroxide ion is what is formed when water donates a proton. OH negative is what we have left over. And so there is our second conjugate pair. And so these Bronsted-Lowry reactions are really just proton transfer reactions. We just have to track where the H positive is going. The particle that accepts the proton is the base, and the particle that donates it is the acid. So let's back up to our first example here and consider the behavior of water. Looking down at this diagram right here, what's the water doing? Oh, the lone pair is grabbing this proton. So isn't this water acting as a proton acceptor? Sure it is. It's acting as a Bronsted-Lowry base. So when water accepts a proton, it forms the hydronium ion, and so here is our second conjugate pair in this reaction. And so you can see that water, which we know to be a neutral substance with a pH of 7, can actually behave as either a Bronsted-Lowry base or a Bronsted-Lowry acid. And so it's key to understand that when we define acid and base by a particular theory, then as long as a substance fits that definition, it's considered an acid or base according to that theory. And so water, even though we know it to be a neutral substance, is actually acting as a Bronsted-Lowry base because it fits the definition of a Bronsted-Lowry base. And similarly down here, it's acting as a Bronsted-Lowry acid. So it does happen on occasion that substances, a species, can behave as either a Bronsted-Lowry acid or base. And so I've given you the term here, amphoteric, and so amphoteric species can behave as either a Bronsted-Lowry acid or base. So I'm asking you now to practice that proton transfer and identify the acid-base pairs as you apply Bronsted-Lowry theory. You'll notice that in the first example I've used a single arrow forward. That's because nitric acid is a strong acid. In the rest of them, I've used an equilibrium arrow, which we'll discuss later. Okay, so the HNO3 definitely has an acidic hydrogen up front, and so it's going to lose that H. It's going to donate it, right? And it's going to lose a positive. So what was originally a neutral charge here is now going to lose a positive. So 0 minus 1 actually equals -1. So there's the -1 charge on the nitrate ion. What's happening to the water here? Well, it's grabbing the proton. So H2O becomes H3O. And in gaining that proton, or H positive, what was a neutral charge here now goes up by 1. So that 0 increases by 1, and so we have the +1 charge on the hydronium ion. To pair them up, the HNO3 formed the nitrate ion when it donated the proton, and the water, when it accepted the proton, formed the hydronium ion. You will notice that Bronsted-Lowry acids, so HNO3 is behaving as a Bronsted-Lowry acid, you will notice that it produces hydronium ions in solution. So in producing hydronium ions, we have an acidic solution. So we'll see a pH lower than 7. So HNO3 is the acid, whereas the nitrate ion will be its conjugate base. Water is behaving as the base, forming the hydronium ion, which is its conjugate acid. And so that's what I'm asking you to do, to go through all of these reactions and transfer a proton. So in the next case, I have water colliding with water. We know water is amphoteric. It can either donate or accept a proton. So pick one to do each and write what's left over. So if I pick the first water here to lose one of its H's, then that's going to form OH, right, with only one hydrogen. And that neutral charge, as it loses a positive, becomes OH negative. What happens to the water that gains the proton? Well, H2O becomes H3O, and the neutral +1 becomes H positive 1. And so the way I explained it, I had this water forming the hydroxide. So this water I showed to be acting as an acid because it donated its proton, which means the hydroxide is the conjugate base. And here, this water molecule behaved as a Bronsted-Lowry base in order to form the conjugate acid. Okay, so we keep going. As long as you have an H up front in the substance, you can donate it. So that H will act as an acid. Here you have an H up front, go ahead and donate it. So have HS negative behave as a Bronsted-Lowry acid. In part E, because you see that negative charge, an anion will act as a Bronsted-Lowry base, and so you'll notice that HS -1 is actually amphoteric. In part D, you're going to have it behave as as an acid. In part E, it will behave as a base. The phosphate ion, seeing that negative charge and the fact that there's no hydrogen to donate, is definitely going to behave as a Bronsted-Lowry base. And the bicarbonate ion, having this H up front, can donate it. So in G, you can have it behave as an acid. And in H, you can have it behave as a base. HCO3 negative is another amphoteric species. For question I, J, and K, you'll notice that all of these are nitrogen-based compounds. I is hydrazine, N2H4, and so we have lone pairs on the nitrogen that will be able to grab or accept protons. And so N2H4, these nitrogen-based compounds, behave as Bronsted-Lowry bases. Same with the organic amine. Again, the lone pair on the nitrogen will be able to grab a proton from the water just like ammonia did. And here in example K, again, it will behave as a base. Now you'll notice I didn't put, in example K, I didn't put water with it. And that's a nice thing about Bronsted-Lowry theory. In Arrhenius theory, the solvent has to be water. But Bronsted-Lowry theory can explain the proton transfer or acid-base reaction when water is not involved. And so K is an example of that. So I'm going to challenge you to complete the right side of these equations and pair up your conjugate acid-base pairs, and then check back with the video. Okay, so you can check your work. Remember, we're always transferring the proton. When a substance donates an H, it also loses +1, so subtract 1. So for example, in D, this H is being donated. We also have to take the charge and subtract 1. So now it becomes -2. So here's our 2 negative charge. Pause the video if you need to because I'm scrolling up. Okay, so if you have any questions, jot them down. But again, you're trying to transfer the proton. The base will accept it. So add an H to the formula and increase the charge by 1, and the acid will donate it. So take away an H and subtract 1 from the charge. Okay, last little bit here. The acid ionization constant, Ka, and the base ionization constant, Kb. So here I have the general formula of an acid, HX. So X negative is just any negative ion paired up with hydrogen in an acid. And so you can go ahead and complete the right side of this equation using Bronsted-Lowry theory. Okay, having done that, we've transferred the proton and formed the hydronium ion. Now, follow your rules for writing the equation for K, and this time we'll call it Ka, because this is a Bronsted-Lowry acid. HX is a Bronsted-Lowry acid. So the Ka for HX will be the expression that you write, omitting any solids and liquids. Okay, and for the bases, we're going to have B behave as a Bronsted-Lowry base, which means it's going to gain a hydrogen and a positive charge, right? And actually, maybe I will just slide that over just so that it really doesn't matter, but I'm showing the hydroxide ion that's formed and that base gaining its H positive. Okay, so Kb we can write as the concentration again of the aqueous products divided by the reactant concentration, omitting the water that is a liquid. And so as practice, to give you added practice, I'm suggesting that you write Ka and Kb expressions for the Bronsted-Lowry examples above. So all of those examples that you did here, so going back up here, as long as the substance right here behaves as an acid, then you're writing a Ka. So here you'll be writing an expression for Ka of nitric acid. Here you'll be writing an expression for Ka of water, which we actually, from the autoionization of water, call it Kw. This one will be a Ka. The next one down here, H2S is behaving as an acid. You'll write an expression for Ka. HS negative in part D behaving as an acid, Ka. In part E, it's behaving as a base, call it Kb. In question F here, the phosphate's behaving as a base, call the expression Kb. In G, bicarbonate's behaving as an acid, call it Ka. Kb for bicarbonate here, and Kb for the N2H4. What's left? The Kb for the methenamine here. And then here we have the ammonia and the hydrochloric acid. So we have demonstrated the proton transfer here, but we can show this just as an equation for K. So really Ka and Kb we're concerned about for A through J. Okay, so you can correct your answers following down for the various equations. Really, I'm just following the same rules that we've always done for writing expressions for K. I'm omitting any solids or liquids, so in this case, water is omitted every time. Okay, and the last thought I'll leave you with is just the idea of interpreting the magnitude of Ka or Kb. So here's an expression for Ka for our general acid HX, right? What would it mean if Ka is very, very large? Very large. So how does this quotient become very, very large? I would suggest to you that it means that the numerator is very, very large and the denominator is very, very small. So that means that we have a great number of ions in solution compared to the acid molecules. And so in fact, when Ka is very, very large, this acid is a strong acid. So the idea of 100% ionization. So we'll be visiting acid-base strength in the next lesson, or coming up soon. Now with Ka being less than 1, then perhaps, right, our numerator is going to be smaller than our denominator. And so we have few ions, right? So maybe 1 to 5% ionization. And so these are our weak acids. And so you will find an appendix in the textbook that lists Ka values and Kb values. And you'll notice that at the top of the Ka table, there are some very, very large Ka values. Those are your strong acids. Once they start to quantify them, times 10 to the negative 3, times 10 to the negative 5, times 10 to the negative 9, times 10 to the negative 11, now we're into the weak acids. Similarly, you can check the bases, and you'll notice there are Kb values provided for many, many weak bases.